Okay, good morning. Let's get started. So we were discussing about in the last class about the unsteady diffusion, right? Unsteady conduction, that is unsteady conduction equation. We have also considered a Cartesian mesh, right? And discretized the unsteady diffusion equation, and we found one kind of an equation which has an interpolation, right, between 0 and 1 levels, right, or t and t plus delta t levels. We arrived at an equation that looks like the following. Okay, so that was rho phi p, right? I am dropping this superscript 1 here, minus rho phi p 0, right, times delta v, right, equals on the right hand side we have what? It was f times sigma, right? How much was it? It was gamma grad phi f dot af, where again the superscript 1 is dropped, plus we have 1 minus f times sigma gamma grad phi 0 f dot af, right? This entire term is multiplied with multiplied by what? Delta t, and then we have plus we have a source term, right, that is also has some f times sc plus sp phi p at 1, right, plus 1 minus f times sc plus sp phi p at 0, and these two terms are multiplied by what? Delta v delta t, right? That is the equation we have. And then we also kind of looked at how does the discretization of the diffusion fluxes kind of helps us rearrange this, further simplify. So that is what we looked at. Okay, now can you help me write down the final discrete form from here so that we can continue? So that is basically, if we rewrite this as if we collect the coefficients for phi p, right. So the coefficients for phi p would be and also you divide the entire equation with delta t, right, and collect the coefficients for phi p. So that would be what? You have one contribution coming from this term, right, that would be rho times delta v upon delta t, right, and then we have a contribution coming from phi this term, right, gamma grad phi at 1, there will be a contribution to phi p, right, all of that will have a minus sign. So when they come to the left hand side, it will all become plus. So we have plus what? F times sigma a and b times phi p 1, that is what we will have, okay. And what other contributions come to phi p? From the source term, that is sp term, right. So I would call this as sp1, sp1, and then this is sc0 and sp0, okay. So this will be minus, this will be a minus f times sp times delta v, and there is no delta t because we have divided with delta t, okay. So this is the term that we have, equals what will be on the right hand side now? Of course, let us collect the terms for phi p 0, right. So the first term is phi p 0 would have is the rho delta v by delta t, right, that is the leftover term on the left hand side. This comes to the right hand and it will become rho delta v by delta t. And what other terms contribute to phi p 0? 1 minus f times gamma grad phi 0. So essentially this term, right. Now out of that term you have central coefficient which is phi p 0, and the other coefficients are phi nb, which goes to something else, right, they go to phi nb 0. Okay, so that would be what? That would be plus or minus? Plus, right, that will be plus or minus for phi p 0? It will be minus, right, because you will write phi east minus phi p, so you will have a minus. So this will be minus 1 minus f, right, times sigma a and b times phi p 0, right. Of course, you have one more contribution coming to phi p 0. What is that? sp term, which I am not writing here, okay. I would write it in the b term, fine. So we have this term plus what else will be there? What other terms do you get? You get of course again from the first term from here you would get phi and b, right. That would be how much? That would be f times sigma a and b, phi and b, right. That is what we would get. And then plus you have another term coming from here, that is what? 1 minus f times sigma a and b, phi and b 0, right. That is what we will have. Plus I have all the remaining source terms, right. So, we are done with all these terms, isn't it? The diffusion fluxes we are done, gamma grad phi terms, right. That is all accounted for. Now, what is remaining is the source terms. Out of the source terms, we already sent the SP phi p term to the left hand side. So, what remains is f times SC, okay, plus 1 minus f times SC 0 plus SP 0 phi p 0 times what? Delta V, okay. Now, there was one question yesterday, okay, SC and SC 0 they are the same, right. Can we just cancel them and then write SC 0 and things like that. So, one thing you have to kind of think about this thing is SC and SC 0 the same? Are they the same? Okay, now that is where you have to kind of think. So, we are talking about here an unsteady equation, right, and if you end up with solving iterations per every time step, then would SC and SC 0 be the same? It will not be, right, because you have now two iterations. One is the outer iteration, which is the time stepping thing, and you have the inner iteration, which is to solve a linear system. In that context, SC 0 would be different from SC 1, isn't it, because you would be using the star values as you update your SC 0s, right, and SC 1 will remain the same, right. You see that. So, you have to understand the difference between SC and SC 0 in the context of time stepping schemes, okay. Think of it, we will come back to that later again when we write down the equations, okay. So, as a result it is not the same. Of course, somebody when there was a question yesterday, the f we have that we have used here in these two and the f we have used in these two, could they be different? Yes, they could be different, right. In which case the kind of interpolation you would use or the scheme you would use for the diffusion fluxes would be different from the scheme you would use for the source terms, that is allowed. But as far as the at least the present discussion is concerned, we are assuming that you use the same scheme for discretizing diffusion and the source terms, okay. But this is very much possible, in which case you will use some f1 and f2 and so on, okay. If it is not the case, then I am going to kind of tell that diffusion fluxes are discretized with so and so such and such scheme and with source terms with such and such scheme, okay. So, that we will kind of tell you, fine, okay. So, this looks good. Now, let me rewrite this thing. So, we would like to call this coefficient as some AP0, okay. Then I can rewrite this as what? This would be AP times phi p on the left hand side equals from the two terms that we have here, can I rewrite this as sigma a and b times f times phi and b plus 1 minus f times phi and b 0, is that okay? I just club the two sigmas, right. Here again a and b are the same, right. Somebody, there was a question yesterday, can a and b be different? They can be different if you have gammas being different, right. So, which we are not considering at the moment. We are assuming that the gamma we have is only a function of space, but not a time function of time or anything else, okay. Fine. So, we can rewrite these two. Then what else? What other terms are remaining? Plus we have this first guy, that is AP minus 1 minus f times sigma a and b times phi p 0 plus we have b, right. That is our simplified equation, okay. So, that is our general equation for unsteady diffusion equation, right. Is it correct? Okay. Then what about what are these coefficients? What is AP0? Rho delta V by delta T. What is AP? AP is what? AP is this entire term, right. That is basically this entire term, right. That is what? AP equals AP0 minus F times SP, is that what it is there? Minus F times SP delta V, what else? Plus F times sigma A and B, plus F times sigma A and B, okay. What else? B, right? What would be B? B is the source term, that is F times SC plus 1 minus F times SC0 plus SP0 Vp0 times delta V. Now, what about the coefficients? A east, A west, all those things? They are the same as what we had in the steady diffusion equation, right, for a Cartesian mesh. So, this was A east equals, how much was A east? Gamma east delta y by del x e, and A north would be gamma north delta x by del y north, and of course, you can complete A west and A south as well, okay. So, those are your A and B values, okay. Fine. Questions till now? This is basically kind of a recap of what we learned yesterday. Okay. So, then let us now look at different schemes. So, you can get we are going to discuss kind of 3 different schemes. One is the explicit scheme, which is basically you set the interpolation factor f equals 0, and that is going to give you an explicit scheme, okay. Now, if you set f equal to 0, can you tell me what will be the resulting equation? Resulting equation will be AP Vp equals, what will be on the right hand side? F equals 0, how much? Sigma A and B, Phi and B 0, because the first term would drop out, right. So, this will basically go to 0 because F is 0, right. So, only term that remains is this guy, A and B 0. What else? Plus what else? F equals 0. AP minus sigma A and B, would that term be there or not? It will be there, right, okay. So, that will be what? Plus AP minus sigma A and B times how much? Vp 0 plus some B, right. Okay. Now, what is AP? AP is how much? AP is AP 0, because if you look at AP this term is there, right. Oh no, not this term, right. So, you have AP contains AP naught plus this is now 0, this is 0 because F is 0, right. So, AP equals AP naught. So, AP equals AP naught equals rho delta V by delta T. Of course, A and B's are the same. What about B? B is F times SC, this is 0, right. What about the remaining term? This will survive. So, this is SC 0 plus SP 0 times Vp 0 times delta V, right. That is B, correct. Everybody okay with this? Okay. No mistakes. All right. So, now let us look at this equation and make some comments, okay. What is the first thing that you see in this equation? What is on the right hand side? Is everything on the right hand side known or unknown, or is it a mix? Everything is known, right, because you have all of them evaluated at what time level? At 0. So, this is phi and B 0, phi P 0, and B contains all the 0 terms, right. So, everything on the right hand side is known, right, and what is the unknown here? Only on the left hand side, phi P is the unknown, that is at the current time level, right, that is at T plus delta T. So, that means if you were to make some comments, first comment is the right hand side of let us call this as some equation, okay. Let us call this as some equation 1. So, right hand side of equation 1 is completely known, right. Right. So, that means the value of phi p at t plus delta t can be found by substituting phi p t values, right, in the RHS, right. That is what we can do, correct. That means it is a simple substitution. You know what is phi p 0, you just plug it in, calculate what is phi p, right. Do we need to solve a system of linear equations here? No, because we are going cell by cell, and every cell you just substitute what is there in that cell in the previous time step. This is much easier, isn't it? Now everybody can code very easily, right. Okay, so this is there, okay. That means we do not have to solve for, no need to solve a system of linear equations, right. Okay, that is good. We do not have to solve for system of linear equations. What about Scarborough criteria? Does it satisfy Scarborough criteria or not? We do not care if it satisfies or not, right, because we are not solving for a system anymore, right. So, we do not really care whether it satisfies Scarborough or not, because we do not have to solve for Ax equal to b, right. Of course, we will be worried if the iterations do not converge, right. So, there will be something that is equivalent of Scarborough criteria that we will see, okay. So, Scarborough is not relevant here, okay. Fine. Okay, what about the behavior as we approach, let us say we are trying to solve a problem for which there is a steady state solution exists, okay. So, we know that there is a steady state solution, but we started off with this unsteady diffusion equation, okay. You have started off with this thing, but you know that there is a steady state solution that exists. So, in that case, what will be the equation in the limit of steady state? Let us say as we in the steady state limit, what will happen to the discrete equation? Which coefficients would go to 0? AP naught, and what about AP? AP also goes to 0, right? AP is gone, AP naught is gone. So, what are we solving? Okay, so essentially these two would go to 0 because it is kind of a steady state. Then what will happen to the remaining parts of the equation? That means this term is gone, right, and this term is gone. What is the resulting equation? You have phi p 0 minus sigma a and b, this goes to the left hand side, right. So, essentially you get sigma a and b phi p 0 equals sigma a and b phi and b 0 plus b. Does it look familiar? This is nothing but your discretized steady state diffusion equation, right. So, essentially we are recovering our steady state equation in the limit of steady state from the equation, okay. Okay, that means in the limit of steady state, that means AP and AP naught both tend to 0. As a result, the equation we get by rearranging these terms is nothing but send this guy to the left hand side, right. So, that would be sigma a and b phi p 0 equals sigma a and b phi and b 0 plus b, right. This is our original equation in the first place for a, if you had started off with a steady diffusion, okay, fine. Now, what about this is from the point of view of the equation. Now, let us say your iterations converge or your time steps converge and you obtain a steady state solution, okay. As your time stepping converges to a steady state, what is that you would obtain? Which quantity becomes unchanging? Phi p and phi p naught, would they become the same if you have reached a steady state, right? Essentially, okay, that means phi p equals phi p naught. Then what will happen to this equation? Phi p equals Phi p naught. So, which terms get cancelled? AP Phi p would be the same as AP Phi p naught, right. Essentially this term goes away, then what remains? We get the steady state equation, right. That means as this equation approaches, as the problem approaches a steady state through iterations, through time stepping, then you are recovering the original steady diffusion equation, right. That property should be valid for any time stepping scheme that you construct. Do you see that, everybody? Right, as Phi p equals Phi p 0, AP Phi p would be the same as AP Phi p naught on the right hand side. As a result, the only term that survives, or the terms that survive, are the sigma NB Phi NB 0 minus sigma NB Phi p 0 plus b, right, which you can rearrange to read it as the same thing as before, right. So, essentially this means Phi p equals Phi p naught, right. Then you would recover the same equation, that is sigma A and B Phi p 0 equals sigma A and B Phi and B 0 plus b. This would be the same equation as we got before, right. So, essentially if there is a steady state to your problem, then your unsteady solution or the discretized equation would also converge to that steady state, okay, by satisfying the original equation. Yes. In the case of second one or first one? First one. No, essentially you do not have terms coming from AP and AP 0, because what was the, how does these terms are coming about? These are coming about because you have this term which is partial phi rho phi p, right, partial t of rho phi p. Essentially you are you have a steady state, so there is no change with respect to time. As a result, this goes to 0. So, the two terms that got out of this thing are the rho phi p delta v and rho phi p 0 delta v, right, which manifested into AP and AP 0 into our equations, right. Of course, another way to look at is you take in the context of steady state, your delta t kind of goes to infinity, right. You are looking at a steady state, so you are essentially independent of the delta t at a very long time. As a result, AP and AP 0 kind of go to 0, both of them, right. Delta t is time, so that is why you should not look at it that way, but that is the only time scale you have. So, in the limit of a steady state, you do not have any time stepping that is coming into play, right. As a result, you do not have these coefficients AP and AP 0, which came about because of this unsteady term, that is partial t rho phi p, right, because if this goes to 0, then you do not have these terms coming into play at all, right. This is AP and AP 0 would not be there. Other questions? Okay, fine. So, let us make some more comments. So, we see that it kind of converges to the same solution. So, this property has to be satisfied by by any time stepping scheme okay, that is constructed, okay, or used, fine. So, all the time stepping schemes that you would come up with should satisfy this criteria. Now, we will see that we have not done it. The order of accuracy of this scheme is only first order, okay. This is only order delta t, this is only first order accurate. So, that means as you refine the delta t, your temporal error only goes down by order delta t. So, that is not very good, okay. So, you have to take like smaller and smaller delta t. So, this method, the explicit scheme is simple, right, and it is very convenient, okay, to use. So, that is why explicit schemes are kind of used in most of the computations, but however, there is a drawback. However, the drawback is the restriction on delta t is a drawback, okay. So, that means you cannot take any delta t that you wish. Okay, so you have to follow one particular condition. So this basically only conditionally stable. That means delta t cannot be arbitrary. Okay, delta t cannot be arbitrary. Okay, so we will come to this point through two different ways. One is when we do the von Neumann stability analysis. The other one is by looking at the equation. Okay, it's kind of just by looking at the equations we can heuristically say what will happen to this thing. Okay, so if you look at the equation, shall I will just write it down again. Can you help me write it? It's become messy. So AP phi p equals sigma A and B P and B 0 plus what do we have? AP 0 minus sigma A and B times PP 0 plus B. Is that correct? AP phi p equals sigma A and B P and B 0 plus AP minus, yeah, that is right. Okay. So that is the equation we have for explicit scheme. Now, what about the coefficient for phi p 0, that is AP 0 minus sigma A and B? Is there a possibility that this coefficient would become negative? Can it ever become negative? We know that sigma A and B's are always positive, they are all positive. What about AP 0? Is it always positive or not? It is positive, but can this become negative? It can. So, if under what conditions can this become negative? If AP 0 is less than sigma A and B, this would become negative, right. So, this will become a this leads to negative coefficient for phi p 0. Okay, so it becomes negative. Now, why do we care? We care because if this coefficient becomes negative, then what will happen to phi p? Let us say we have a minus in here. Let us say in one particular delta t at time t, phi p 0 is kind of a large value. Okay, it increases because you have a negative. What will happen to the phi p at the current time level? This would go down, right? As this phi p 0 is increasing with time steps, this will go down, right. So, this kind of behavior is not acceptable in the context of parabolic PDEs. So, if you have negative coefficients, an increase in value of phi at one time level would lead to a decrease in value of t at the next level in the same cell. Okay. So, this kind of behavior is not acceptable. So, this is not acceptable in the context of parabolic PDEs. Okay. As a result, we have to make sure we kind of meet with this condition, and the condition would be what? Would be AP 0 has to be either greater than or equal to sum of the A and I bus. Okay. So, that means AP 0 has to be greater than or equal to sigma A and B, right. So, that is the condition we have to satisfy. So, we can show that this condition boils down for a uniform mesh with constant properties. It boils down to something that looks like this. Delta t that we have should be less than or equal to rho times delta x square divided by 2 d gamma, okay, where d is either 1, 2 or 3 depending on the dimension of the problem. So, if you are looking at a 1D problem, this is rho delta x square by 2d gamma. Now, we will prove this little later, okay, using von Neumann stability analysis. You can of course also prove this by just writing what is A and B and what is AP. You can substitute the definitions rho delta V delta T and gamma delta Y by delta XE and so on, and then prove that this condition is satisfied, okay. So, that means you cannot take any arbitrary delta T, it has to be dictated or should be smaller than this condition, okay. So, this in the literature is known as the von Neumann stability criterion, okay, which has to be satisfied by the explicit scheme in order to get converged solution, okay, in order to get physically possible and converged solution. Okay, now all right, so this condition is too restrictive because your delta t now goes as delta x square, that is too restrictive, because if you keep refining your mesh, you have to take it much smaller than the square of the delta x. So, that is very restrictive, okay, because you can only go with a very small delta t, you can march ahead. So, it is very restrictive, that is why the explicit schemes are not used to a great extent, okay, because of the limit on the delta t, okay. And also as delta x goes down, delta t goes down much faster, right. Okay, so this is kind of a big restriction for the explicit schemes. We will do this again in the context of von Neumann stability analysis, okay, that will be coming up in the next few lectures. Okay, fine. Questions till now? Can delta t be negative? Can delta t be negative? Can it be negative? Cannot be, right? Yes. Which is? AP, is it AP or AP naught? AP naught, right? This one. Oh, in the actual equation it is AP, is it? Which is the actual equation? You mean the one I have written here? This is a mistake, this should be AP naught, right? Isn't it? That should also be AP naught. Anyway, for the context of explicit schemes, AP equals AP naught, right? AP is same as AP naught for the context of explicit schemes. Other questions? Why is that essentially an increase? Essentially, these kind of solutions are not supported by parabolic PDEs. You cannot have, for example, if you in the context of diffusion problems, we saw that everything has to be bounded in the absence of source terms, right? Similarly, when you have a parabolic PDE, you cannot have an increase in value at one time step causing a decrease in value at the next time step as you for the same cell, okay. Now, why is it a problem? This actually leads to, eventually this leads to what? Leads to oscillations, which will lead to divergence, right. Essentially your solution will kind of oscillate, will start oscillating, and then it will eventually diverge. That is what actually is dictated by this. We will try this with an example in the assignment, okay. We will have where delta t will be given to be certain value. If you start taking it to be larger than the von Neumann stability condition, you will see that the solutions you would get are kind of display oscillatory nature, and eventually they will diverge, okay. Essentially you would get very large values. But this behavior is perfectly fine if you have, let us say, a hyperbolic PDE, right, or if you have, let us say, a source term or a sink term and things like that, okay. Other questions? Yes. Okay. So, you want to run a simulation backward in time. So, we have this principle of causality, right. What is principle of causality? What is principle of causality? You have a cause and effect, right. It is not effect and cause, right. For example, only today can influence tomorrow, today cannot influence yesterday, right. So, if you want to run a simulation backwards, I do not know what does it mean. It is as simple as going back to yesterday, right. And if you can put it physically, I would be happy to answer. Okay. 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 Oh, okay. You want to go back by a small time step for the simulation. I don't know. That is essentially same as you start off with the old condition and proceed in the future, right. Instead of going back, you start off with whatever is the time and then you proceed forward, right. That is the main difference between time stepping and spatial differences, isn't it? You don't have, so spatial schemes, if you look at, have, you can go both ways, right. You have dependency on I plus 1, I minus 1, I minus 2, I plus 2 and so on, but delta t you have only dependency on either t, t plus 1, t plus 2, right, not on the previous. You can have on the previous, but they should be known, right, but you do not go in the backward direction, right. Other questions? No? Clear? Fine. So, you can now code the explicit scheme, right, essentially it is calculation of Vp from the old values, right, very straightforward. What will be value of D for an axisymmetric case? That we have to see. Probably it will be slightly, maybe it will come out to be 1. I don't know. I haven't solved it. Maybe that's a good question. Okay. What is the value of D for axisymmetric? Maybe you can calculate and tell me. Okay. What is D for axisymmetric? Now I have one question. So let's say we have no iterations, right, which is kind of a good news. So why don't we solve every steady state problem using unsteady with this explicit scheme? Why should we bother ourselves to write this TDMA, line by line TDMA, all these things, and or Gauss-Seidel? Or can't we just suppose or pretend that all the steady state problems that we want to solve, like till now, we would say that they are all unsteady, and then we will just add this extra term and then start using this explicit scheme. Wouldn't that be easier? Wouldn't that be faster? Is the question clear? Right, we wanted to solve for del dot gamma grad phi plus S phi equals 0. So essentially we want to solve for a steady state problem, right, for which we know that the problem itself is steady state. So what I am saying is we add this, we say that we pretend that this is not steady state, we start off with partial phi rho phi, right, and then we construct an explicit method using explicit scheme. I would come down and then use these equations and just keep substituting with some guessed initial condition. I would just keep updating the values from here. Wouldn't that be faster and easier than solving for a steady state problem in the first place? Yeah, we stop at Vp equals Vp 0. Is it not easier? That is something for you to think. Okay, is this easy or is this computationally cheap, right, or is it correct? So that's what question is clear, right? Okay, fine. Okay, this is for you to think. All right, let's move on to the next method. That is the implicit method, the fully implicit method. You would obtain a fully implicit method if you set f equals 1. Okay. So in the previous case we kind of assumed that f equals 0, that means the Vp 0 values, 0 level time values prevailed over the entire time step, right. Here we are assuming that f equals 1, that means over the entire delta t, the phi values at t plus delta t prevail over the entire delta t, right, that is what we are assuming. Now essentially substitute f equals 1 and tell me what would be the equation. So to go back to the original equation, substitute f equals 1, again this should be sum AP phi p equals f equals 1. So second term drops out on the right hand side, the first term will remain. I think so that is what would be on the right hand side, sigma a and b p and b plus AP naught AP naught times Vp naught, that is all, because the second term has f times something, so that is 0. So AP naught Vp naught plus b, and what would be b? SC delta V, that is all. okay. And what about AP? Is the same as AP naught? No, it is not, okay. What is AP? You will have sigma A and B plus AP naught minus SP delta V, is that correct? Huh? And AP naught is how much? Same as before, that is rho delta V by delta T. Fine. Okay. Now what can you say about this equation? So this equation you would solve at a particular time step, right, for a particular delta T. So what kind of if you want to make some comments, what can you say about this equation? Is it can you substitute for Vp values and get it similar to the previous case? You cannot, right, because Phi and B are unknown. So what would you need here? For every delta T, you need to iterate, or essentially you need to solve for a system, right. So every delta T requires every delta T need to solve a system of linear equations, okay. That means you have to use Gauss-Seidel or a TDMA if it is one day, or a line barren TDMA for every delta T. Now do you see the two loops? If you are, let us say, using Gauss-Seidel, the inner loop is where you would solve for a particular delta T, and the outer loop is where is your time stepping loop, right. Your delta T is going with by amounts of delta T, right. So there are two loops. Now do you see the difference between SC0 and SC1 in this context, right. You would keep some things the same for the entire delta T, but certain things you would update as you go within the inner iterations, right. So that is where this difference of SC1 and SC0 comes into play, right, okay, fine. So every delta T need to solve a system of linear equations. This is lot more work, right, of course. Then what else? Then the second thing is, if you look at this equation, AP, let us say in the absence of source terms, how does this equation look like? This equation looks like AP phi p equals sigma A and B phi and B plus AP0 phi p0, right, B is 0. So essentially this is nothing but sigma A and B phi and B, where the neighbors are east, west, north, south, and also the phi p0, right. So the previous time level can also be thought of as a time neighbor, right. You have 4 space neighbors and 1 time neighbor. That means we are now back to this original concept of boundedness, right, because AP is now equal to sigma A and B plus AP0, and AP phi p equals sigma A and B phi and B plus AP0 phi p0. We are back to this boundedness what do you say, the problem, right, or the boundedness, what would you say in terms of the property, right. So we have a boundedness property, right, we are back to that. So the boundedness property is now satisfied by this method, right, because now we are back to AP phi p equals sigma A and B phi and B, where NB goes from east, west, north, south and time, and AP equals sigma A and B, where NB goes the same way as it is, right. So that means the coefficients are all will come out to be fractions of AP, right. A and B by AP will be what it comes out to be. That means phi p is bounded by phi and B and phi p0, right. Now will it be not bounded in any context? Let us say source term is still 0. Would there be a condition where it will not be bounded? Let us say you take any delta T. Would there be an effect of delta T on this thing? No, right, because it does not matter any delta T you take, accordingly AP0 will adjust, and then AP will still be sum of sigma A and B, and then AP phi p would be still sum of sigma A and B phi and B, right. That means you would never get this problem of negative coefficients, right, and always it is bounded, which is the property that has to be satisfied by parabolic PDEs. As a result, implicit scheme satisfies this property. Okay. Okay, very good. Now, what is the advantage of the implicit method? We just saw that it has to solve Gauss-Seidel or something like that. Now, where is the advantage coming into play? We are putting in more effort. What is the advantage? We just discussed delta t. Essentially, you can take any delta t that you like, right? And you still get a solution. Now, that does not sound quite right, because you may get a solution which is kind of not infinite, but it may not be accurate if you take a very large delta t. So, the delta t you take from implicit schemes is of course much larger than the delta t that can be taken by the explicit methods, whereas this delta t cannot be very large that the solution is inaccurate. Okay. So, essentially one of the comments is any large delta t can be used. However, if it is too large, accuracy is not guaranteed, but still you would get a bounded solution, you will not get an infinite solution. Okay. However, accuracy is not guaranteed. Okay. But convergence is guaranteed, it will converge to some answer, but it will not be accurate because the delta t is very large. Okay. Of course, we also will prove later that the method is only order delta t. So, if you reduce delta t by half, the error only goes down by half, it is only a first order method. It is only a first order method, right. Okay. So, we have so as a result you kind of use implicit method, but not to a large extent, because we have another method that we will discuss tomorrow, that is the Crank-Nicholson method, which is a combination of these two. So, essentially in the implicit method, the values of t plus delta t prevail over the entire delta t, right. Right, that is phi p1 values or phi nb1 values prevail over the entire delta t, that is what we are considering. Fine. So, we will kind of stop here. We will meet in the next class and discuss about the final method, that is the Crank-Nicholson method. Okay. Thank you.